Now that we know the basics of how to balance equations, in this lesson we're going to look at some tips for reactions that might appear to be a little bit harder, and you can actually get to some balancing equations that are really challenging, but most chemical equations are pretty easy if you know a few tips and tricks. So in this one, we're going to get you a little bit more guidance, and instead of just saying, hey, start with whatever element you want to, we're going to give you some tips about where to start. Okay, so let's look at this first one though. This first one definitely I think is one that we can do from last time. So what I want you to do is we're going to stop the video here. I want you to write it on paper, balance it, and then type in the coefficients. And remember, you need to practice this on paper. It doesn't really make any new learning if you sit here and watch me do it. So it's really important that you do that. You don't have to type in the whole equation, but when you're done, type in the coefficients. Okay, let me show you how I would do it, and I'm going to get a better marker here. Let's see. You remember we divide the world in half. We start with whatever element we want to. Why don't we start with oxygen? I see two oxygens. Looks pretty good, right? Start with sulfurs. Which side needs more sulfurs? Definitely this side, right? The right side. And so what number goes here? I would say an 8. And that will give me 8 of these things. Now I will tell you honestly that I don't typically draw down 8 of these. I just simply go, hey, 8 sulfurs. But if we're going to do that, if we're not going to draw down 8 of these, because it's a little bit slow to do that, but I'm going to do it here just for a second. But if we're not going to draw all these down, we need to start to come into an understanding about that this 8 means 8 of these things, right? So yes, we have 8 sulfurs, and the 8 sulfurs are balanced. But you know that this 8 affected the oxygens too. You can see it clearly down here in the drawings. But of course, the way I tend to do it is I do 8 times 2 oxygens. That gives me 16 oxygens. Let's see if I was right. 2, 4, 6, 8, 10, 12, 14, 16. It does give me 16. So if I multiply those two, I can see how many oxygens there are. So that's 16. So therefore, if I want 16 oxygens on this side, what number is going to go here? Let's see, 8 times 2 is 16. That's right, that gives me 16 oxygens. And what it would represent, and you can see why I don't really want to draw these down, is because for me to draw out 8 of these, 1, 2, 3, 4, 5, 6, 7, 8, it takes a little while to do that. So 8 times 2 tells me there's 16, 2, 4, 6, 8, 10, 12, 14, 16. So if you understand that multiplication trick, you don't necessarily have to draw all these out. All right, and let's make sure the sulfurs are still balanced. 8 and 8, 16 oxygens, 16 oxygens. I've done my check at the end. We're done. By the way, I don't have to put anything here. I could simply write the equation without lines as this. But if I want to put something here, what do I put? 1. And a lot of times, you know, if you're ever entering these into a computer, the computer expects you to put something there. Okay, so let's look at this one. Now this one you may look at and say, oh man, that looks a lot bigger and more challenging. But I have a tip for you. What makes this one look a little bit bigger, other than there's more types of atoms, is do you see that there's a polyatomic ion in it? There's a nitrate ion here, right? This thing is a nitrate ion. And if you see a polyatomic ion, a lot of times it's what's causing the reaction to look a little bit bigger. And so my tip for you is do the polyatomic ions first and treat them as a group. Let me show you what I mean. Do you see NO3 is nitrate? Here's NO3 over here as well. Now, do you see that there are 3 nitrates? Well, over here, there's only 1 nitrate, right? That 3 doesn't mean there's 3 nitrates because nitrate is NO3. That thing is a group. Matter of fact, they usually when there's 1, they don't put parentheses on it. But if you wanted to, you could put parentheses on it, and then it helps you see that there's 1. So therefore, clearly, if I have 3 nitrates over here, I'm going to need 3 nitrates right there. So now that we've done the nitrates, things will go pretty well. By the way, let's do sodium next, Na. Which side needs more sodiums? Definitely the right side. And what number should I put here? 3, because that gives me 3 NAs, right? Let's do chlorines. Which side needs more chlorines? Well, this one has 3 chlorines. That one has 3 chlorines. It's good to go. Let's see. Let's do aluminum. I don't think we've done aluminum. Which side needs more aluminums? Neither. There's 1 aluminum here, and there's 1 aluminum there. We might be balanced. I don't think we messed with our nitrates. Yep. So we're done. We can either leave it as it is, or I can put 1s in those blanks. So you can see how on bigger ones like this, drawing down those every single time I do a new compound can get a little bit tedious. And so understanding that if you have a number in front, it means there are 3 nitrates, right? 3 sodiums. You just do the multiplication trick. Okay, let's try this one. So since you have that understanding, my suggestion is start with the polyatomic ions. But in any case, draw the whole equation down on your piece of paper. You do have to write it down, right? And for some reason, I don't have blanks here. I'm sure they'll show up in just a second. And then I want you to balance it, and I want you to type in the coefficients just in the order that they come. All right, let me show you how I did mine. Remember, this is the dividing line. There were 2 phosphates, right? Over here, there was only 1 phosphate. So what goes on this line? A 2. That's absolutely right. Now let's do strontiums. Which side needs more strontiums? Definitely the left side. That's true. What number goes here? 3. All right, let's do potassium, K. First of all, before we do this, how many Ks do you see over here? 6. 2 times 3 is 6, right? Like if I had drawn out 2 of these, right? Just like because there's 2 of them up there, that would have been 6. So 2 times 3 is 6. So what goes here? 6. That's right. And are we done? Our Ks are balanced. Our phosphates, we have 2 phosphates, 2 phosphates. We have 3 strontiums, 3 strontiums. I think we're done. And if I want to, I can put a 1 on that line. All right, last one before we get to our extra tip here. So I want you to write this equation out on your page and balance it and type in the coefficients you get. All right, we're going to divide things in half. You know I feel like we should start with polyatomic ions. This is the carbonate ion. Oh, we can't really see it, but this is the carbonate ion, which reminds me I'm going to have to switch marker color. Let's just do that. All right, I see 3 carbonates over here, so what needs to go on this line? 3. Yep, I got 3 carbonates. Let's do, I don't know, let's do Fe next. Fe, iron. Which side needs more irons, the left or the right side? Definitely the right side. What should I put here? A 2? All right, let's see. I've got 2 Fe's, 2 Fe's. Looks great. Let's do iodines. How many iodines do you see on the right now? It's not just 3, is it? Because there's 2 of these molecules. So 2 times 3, there's 6 iodines. So I'm going to put a 6 there. All right, are we done and balanced? Let's try silver, Ag. Which side needs more Ags? Well, that has 6, and this has 3 times 2. It has 6 as well. So we might be balanced. I think we are. All right, we're done. Great job. So that's how we deal with polyatomic ions. Now here's my other tip for you. I want you to look at this one. Matter of fact, I'm going to stop the video here, and I want you to try it first, and then I'll give you some tips. What makes this one harder than other ones? It doesn't look as complicated as the one we just did, but I want you to look at this. If we divide it in half here, do you see how this is the first time we've run across an equation where there's one element that's in 2 spots on one side, right? Normally we're saying, hey, look, there's 2 carbons over here, there's 1 carbon over there, let's balance it. But you notice hydrogen, there's one on the left and some on the right, but oxygen, well, this side there's just in one place, there's oxygens there and oxygens there. This oxygen on this side needs to balance all the oxygens on that side. So that's something to keep in mind. It makes things a little bit harder. Now here's my tip with these kind. I will tell you most of the time that atom that's in more than one place is oxygen, almost always. So I leave oxygen to last. But really honestly, the rule should be a little bit broader. Any element that is in more than one place on one side, I leave it to last. And the reason is because almost always it works out without me doing anything. I don't have to think too complicated about things. So if you have an element that's in more than one place on one side of the equation, leave it to last. Okay, so that means let's do carbon first. Which side needs more carbons? The right side. What should I put here? A2 to get 2 carbons, right? Okay, we've done that. Let's do hydrogens. Which side needs more hydrogens? The right side. And since I need 6 hydrogens, what number do I put here? 3. 3 times 2 is 6. That's absolutely right. Now let's do the oxygens. Now over here I only have 2. I get that. Over here, how many total oxygens do I have? Like over here I have 2, right? How many total oxygens do I have? 2 times 2 is 4, right? So there's 4 oxygens from this thing. And how many oxygens here? There's 3, right? Because that's a 1, so 3 times 1 is 3. So I have 4. 2 times 2 is 4. 3 times 1 is 3. I have a total of 7 on this side. Ugh. All right, so the reason I'm going, oh, that's not good, is because then we get to our next tip, which is a lot of times you think about it. If I came over here and I needed this to be 7, if it was 6, it'd be easy, right? I'd just put a 3 there. If it were 8, it'd be easy. I'd put a 4. But if it's 7, it's an odd number. Doesn't it feel like I need, like, if 3 times 2 is 6 and 4 times 2 is 8, I need like 3.5 here, don't I? But we can't have half molecules. We can't have half atoms. Yes, 3.5 times 2 is 7, and that would balance it for us. But we can't do that. So here's my tip to you. If you ever run across that situation where you have to balance something with a non-whole number, then come back through, and wouldn't it be easy enough for me to just double this? Because if it's balanced for 3.5, if I double that, all I have to do is double this, right? There was nothing there, so I'm going to say 2. Double this, make it 4. Double that, make it 6. So if you ever have to balance for an odd number, just double the amount and you'll be able to balance it all. Let's see if it turned out to be balanced. How many carbons do we have? Well, 2 times 2 is 4. Do we have 4 carbons on the other side? Yeah, we have 4 carbons on the other side. Let's see how many oxygens. We have 7 times 2. We have 14 oxygens. Over here, I have to get rid of this and do new work. 4 times 2 is 8, and I have 6. That's 14. Yep, we do have 14. So we balanced it with a fraction, and then we just doubled it all to make it all a whole number. And that's it. That's kind of how you tackle these when there's an element in more than one place. Let's try, not that one. I want to try this one. Let's do this one last one. So I want you to write it on paper. It's a little bit harder. Which atom are we going to leave till last? Oxygen. Definitely a little oxygen because it's in more than one place. And I want you to type in the coefficients you get. Okay, let's try it out. So I'm going to leave oxygen till last. Well, hydrogen, the problem is they're already 2 and 2, right? Don't need to do anything there. Oxygen, there's 2 on this side. Over here, there's 1 there, right? And there's 2 there. That gives me 3 oxygens on this side. Now, if there are 2 oxygens on this side and 3 on that side, clearly we need more over here. Wouldn't you agree? All right, so if this is a 1 right now. If I notch it up to 2, that gives me how many oxygens on this side? 4. All right, that's not bad. Now, if we come over here, we still have 1 there and 2 there. That's 3. Now, we have to make a decision about where to increase the number. I'm actually going to suggest we increase it here, and I want to show you why. Because this is 4, I want you to think about this. If I put a 2 here, well, let me just do it so we see what happens. That would be 4 plus 1. That would be 5. If I put a 3 here, that'd be 6 plus 1. That'd be 7. You notice how if I increase this one, it's always an odd number? So that's why I'm not going to do that one, is because if I do the other one, I can at least make the numbers even. So let's see, I'm going to notch this up to 2. So now 2 oxygens here and 2 oxygens there gives me 4, just like I had over there, and we're good to go. And I think our hydrogens, we didn't mess it up, so if I want to, I can put a 1 there. And that's it. That's how you deal with the tricky ones. If you run across an atom that is in more than one place on one side, leave that one to last and keep working on it. And the other thing is you got to have a kind of a problem-solving mindset. In other words, sometimes I'll look at these things and I'll be wrestling with them a while. You're going to definitely do it in pencil. You're going to need an eraser, because if you're thinking, wow, this one was pretty easy for me, I've definitely got harder ones for you. If you're thinking, man, this was really hard for me, we're going to start with a little bit of an easier level on practice, and you'll see after a while you just get really good at them.